let's just jump right in. If you're a computer science student in India right now, and you're dreaming about getting that day one offer from, Google, Amazon, maybe Meta, then you know the competition is just insane. But what if I told you there's pretty much one skill, just one thing, that's standing between you and that dream offer? And no, it's not about being a Python guru or a Java wizard. It's something way more fundamental. Today, we are cracking the code on data structures and algorithms, or as you know it, DSA.
So let's get real. This is the question we all ask our seniors, right? Dude, is the Google interview really that much harder than the one at Amazon? You hear all these stories, these crazy whiteboard problems, interviewers who push and push until you find the most optimal solution imaginable. So what's the actual deal?
Well, the truth is, while their styles might be a little different, both of these companies are absolutely laser-focused on one single thing: how well you use data structures and algorithms to solve tough problems and how efficiently you do it. That's it. Your DSA knowledge isn't just another subject, it is literally the master key that unlocks the door to both of them.
Now, I know that can sound super intimidating, but here's a little secret. You're already an expert algorithm designer. And I'm serious, you use these things every single day, and you probably don't even realize it. DSA isn't some abstract course you have to memorize. It's a way of thinking, and we're about to tap into that intuition you already have.
Okay, just imagine this for a second. You're the class monitor, right? And someone just dumps this monster stack of 200 test papers on your desk and says, sort these by roll number. The rookie move is to just start at the top and go one by one. But you're smarter than that. You grab a friend, you split the pile right down the middle, and you each sort your own stack. Then, all you gotta do is merge those two already sorted piles together. Boom, done in like half the time. You know what you just did? That's a world-famous algorithm called merge sort. See, you just found a smarter, faster way to solve the problem.
So that's the key, really. An algorithm is just a set of steps to get something done. That sorting trick, that's an algorithm. The exact steps you followed to make the perfect cup of chai in the morning, yep, that's an algorithm too. In programming, we just have to be super precise about those steps so we can make them as fast as possible.
But of course, an algorithm needs something to work with. You can't just have a recipe, you need your ingredients organized. And this quote, wow, it hits the nail on the head. Trying to write a complex program without the right data structure is like trying to build a house with nothing but a giant pile of bricks and no blueprint. It would just be total chaos.
Data structures are that blueprint. They are the frameworks, the shelves, the filing cabinets we use to organize our data so our algorithms can work their magic. Think about it like a huge library. If all the books were just thrown in a giant pile in the middle of the floor, trying to find one specific book, the algorithm, would take forever. But because they're organized by genre and author, a data structure, finding any book is incredibly fast.
So let's see how this all builds up. Data structures really come in two main flavors. First, you've got your primitive types. Think of these as your individual Lego bricks. A single number, a single character. They store just one value, and the computer can access them really fast. And then you have the non-primitive structures. This is what you actually build with those bricks. These are the complex creations like arrays, linked lists, and trees that hold whole collections of data.
And what's so cool about this is how simple the core idea is. I mean, look at this. This humble little thing is called a node. All it does is hold one piece of data and a pointer, which is basically just an arrow, to the next node. From this one tiny, simple building block, we can build these mind-blowingly powerful structures like linked lists and trees that power everything from your Instagram feed to Google Maps. It's amazing.
Okay, so we have our blueprints, the data structures, and we have our instructions, the algorithms. But when you're sitting in that Google interview, there is one more thing that matters more than anything else: speed. How do we actually prove that one way of solving a problem is better, faster than another?
Let's use another analogy. Say you need to find the word programming in a massive dictionary. The slow way, the brute force way, is what we call a linear search. You start at page 1, word 1, and you just keep reading. Ugh, that could take hours. Now the smart way is a binary search. You jump straight to the middle of the dictionary. Is programming before or after the words on this page? After? Great. You just threw away the entire first half of the dictionary. You do it again and again, and you find the word in seconds. That huge difference in speed, that's the whole game.
So this whole science of measuring efficiency has a formal name. It's called time complexity. And we talk about it using something called Big O notation. Now listen, don't let the name scare you off. It's just a simple, standard way for programmers to talk about how an algorithm's runtime is going to change as the amount of data you give it gets bigger and bigger.
Let's break down the big ones with some easy analogies. First, you've got O of 1, or constant time. Think of a food app showing you the top 5 recipes. It doesn't matter if the app has 100 recipes or 10 million, right? The work to show the top 5 is always the same. Then there's O of n, or linear time. This is like finding one student in a classroom of n students. The more students, the more time it takes. Makes sense. Then there's O of log n, our amazing dictionary search. This is the holy grail. The work barely goes up even if the dictionary grows to 1 million pages. But then you have O of n squared, quadratic time. Imagine having to compare every student in a class to every other student. As the class gets bigger, the amount of work, it just explodes. You want to avoid this one at all costs.
So why do companies like Google and Amazon obsess over this stuff? Because when you're working at their scale, the difference between a pretty good O of n algorithm and a brilliant O log n algorithm isn't just a few milliseconds. It's literally millions of dollars in server costs and the difference between 1 billion happy users and 1 billion frustrated ones.
And this brings us right back to our original question. As you can see, Google interviews are kind of legendary for being harder, with a massive focus on you finding the absolute most optimal solution in terms of time complexity. Amazon tests DSA hard too, don't get me wrong, but they might balance it a bit more with other things. The bottom line is, you have to be ready for both. So let's just nail this down. Mastering DSA is non-negotiable for 3 huge reasons. Number 1, it teaches you to write optimized code that saves companies time and money. A lot of money. Number 2, it gives you the mental toolkit to look at a huge, impossible-sounding problem and break it down into small, solvable steps. And number 3, let's just be blunt about it. It is the number 1 thing you'll be tested on in your first-round interview at every single top tech company. Period.
Okay, so you get it. DSA is absolutely crucial. So how do you actually go from knowing this stuff in theory to walking into that interview and completely crushing it? Well, it's not about memorizing hundreds of solutions. It's about being strategic. And here is the real secret. The key isn't to solve 1,000 random problems. It's to learn the underlying patterns. It turns out there are about 16 core coding patterns that unlock the solutions to almost every interview question you'll ever face. Once you master a pattern like 2 pointers, for example, you won't just solve one problem. You'll suddenly be able to solve dozens of problems you've never even seen before. It is a total game changer.
All right, let me give you some rapid-fire pro tips straight from a senior to you. First, stop just reading theory. You need to be on a platform like LeetCode and solve problems every single day. Second, before you write a single line of code, you must be able to explain the time and space complexity of your approach out loud. Third, always think about the edge cases. What if the input is empty? What if it's a really big number? Test for it. And finally, pick the right data structure for the job first. This one choice can be the difference between a genius solution and a total failure. So, there you have it. You now know why data structures and algorithms are the absolute bedrock of a top-tier career in tech. You've seen the concepts, you've seen the real-world impact, and you've seen the path to get there. The only question left is, are you ready to master the how?